Hello everybody and welcome back to another video by Funland Tutorials. In the last videos we have been talking about the properties of relationship, properties of a relation such that we can discuss which properties hold for a particular relation. So we have already discussed the properties of reflexivity, transitivity, anti-symmetry, symmetry and completeness. I will link the respective videos somewhere up in the cards below. Whenever I talk about a particular property, I will be linking the relevant video up in the cards, and I will also link them down in the description box below. So do check them out because the theories will be discussed there. I will just refer to those theories here when I discuss a particular sum that I'll be talking today. So essentially what we'll be doing today is we'll be looking at a particular sum and we'll see how to how to solve these questions and how to approach these questions when they come in the examination. So what are the things that we need to know when we solve a particular question? Suppose we have been asked that we need to check for whether the 5 properties hold. So let me say that the question, so let me just write the question with red. So the question is, we need to check for the properties of the relation, and here we will be talking about the relation is divisible by. We'll be discussing what I mean by that as I progress with the sum, but we'll essentially be checking for the properties of the relation is divisible by defined on the set of natural numbers, that is the set of positive integers. I have discussed before why I call them positive integers and not simply integers, because I want to exclude 0 from this set. So I'll be essentially talking about is divisible by as the relation, and I'll be talking about the set as the set of natural numbers. Now how do I proceed with the sum, or how do I approach the sum? First, let me write down the things that I have been told or given by the sum. So usually, as you can refer to the previous examples, the first thing that we need to understand is what is my R and what is my capital X, because the entire concept is based on these two categories or based on these two concepts. So essentially we'll first need to figure out those two. Here the relation R is essentially is divisible by, so its relation is divisible by, and that is here, that is the relation R. So let me just mark it like this, so that is the relation, this is R. What is the other thing that I need to know? The other thing is the set, capital X. This capital X will be the set of natural numbers. So here X is equal to capital N. This is a simple sum because it considers the set of natural numbers. Now how do I need to, what do I need to do further to check for the properties of the relation? Let us take one relation at a time and see whether it holds or not. Before that, let me define what I mean by is divisible by. Suppose I take any two elements x and y. Now why am I taking two elements? Because if I need to establish a relation between something, I need two elements, right? If I want to establish a relation, I need two elements with which I can establish the relation. So let me take two elements belonging to the set of, not x here, but the set of natural numbers, because it's specified in my question. Now when I say x is divisible by y, here x or y means x is divisible by y. So if x is divisible by y, what can I say? I can say x is equal to ky, where k is some positive integer. So I say k is some positive integer. Here I am denoting positive integer as z, so as not to confuse with the set of natural numbers, though they are actually the same thing. Here actually, to be very precise, when I talk about divisibility, it might include the set of negative integers as well, but since we are dealing with natural numbers, x and y are natural numbers, z cannot be a negative integer, so I am talking about z plus, to be very precise. That is, the k belongs to the set of positive integers. So that is essentially the definition of is divisible by. So let me just highlight that so that I can refer to it in my future parts of the sum. So this is essentially what I mean by is divisible by. Now how do I approach the sum? let me take one property at a time. So let me start with the property of transitivity because it's the first property that we discussed. Let me take with the property of reflexivity. So let us first start with reflexivity. So we will start with reflexivity. Now what was reflexivity all about? Reflexivity was the property which related an element of the set to itself. So if I take any element x belonging to the set of natural numbers, can I say x related to x itself? Can I say x related to x itself? What would that mean? That would mean x is related to kx by the definition, by this yellow highlighted definition. Is that possible? Of course that is possible when k is equal to 1. And 1 belongs to the set of positive integers, right? 1 is a positive integer. So k is possible, it is possible that k takes the value 1. Hence, I can have x is equal to kx. That is, any number may be divisible by the number itself. Hence, reflexivity holds. So, we can say that reflexivity holds. Let us take the next property. So, the next property that we had discussed is the property of anti-symmetry. So, the property of anti-symmetry. Let me just write it in short. So, I'll talk about the property of anti-symmetry now. Now, the property of anti-symmetry said that if I have two elements x and y belonging to the set of natural numbers in as per the sum, if I see that x is related to y and y related to x, that would imply that x is equal to ky. That would imply x is equal to, let me say, k1y and y is equal to k2x. So x is equal to k1y and y equal to k2x. Here both k1 and k2 will have to belong to the set of positive integers as per the definition. Let us suppose that these two are true. If that is true, then what I can conclude is that, so I can conclude that x is equal to k1. In place of y, I can replace k2x. So in place of y, I can replace k2x. What will that give me? That will give me k1 into k2x. So we have x equal to k1 into k2x, or x is equal to, I can write it as k1 k2x. Now since x belongs to the set of natural numbers, so x belongs to the set of natural numbers, I can cancel out x from both sides. So I can cancel out x from both sides and I can conclude that k1 k2 is equal to 1. Here's the problem. K1 and K2 equal to 1, but K1 and K2 are both positive integers. So I cannot have 2 into 1 by 2 or something like that. The only two positive integers that can give the product as 1 is when K1 equal to K2 is equal to 1. You can check that there are no other positive integers such that their product is 1. So I'll have to have K1 is equal to K2 equal to 1. What does that give me? If I have k1 equal to k2 equal to 1, then from these two relations, I can deduce that x is equal to y. What does that give me? That gives me if x related to y and y related to x, then, so let me just highlight, if x is related to y and y related to x, then I can conclude that x is equal to y. What does that mean? That means anti-symmetry holds. So I have anti-symmetry to be true in this case. What is the third relation? The third relation is the symmetry property. So the third relation is the symmetry property. What was the symmetry property? The property was that if x is related to y, I should be able to conclude that y is related to x. Now is that true in this case? If x is related to y, I'll have to say x is related to ky, where k belongs to the set of integers or the set of positive integers. Now from x equal to ky, I can say y equal to 1 by kx, y equal to 1 by kx. Now the thing is, the only way in which 1 by k can be an integer, so 1 by k can be an integer if and only if k is equal to 1. That is, k has to be equal to 1. Otherwise 1 by k cannot be a positive integer. So this entire property does not hold for all values of x and y. That is, it's not true for all values of x and y. So only if x is equal to y, this property holds. It's not true for any combination or any choice of x and y that you take from the set of positive integers or the set of natural numbers that we had started with as the sum. that is the set of natural numbers. So in this case, the set of the symmetry property does not hold. That is, the set of the symmetry property is not satisfied in this case. What is the fourth property? The fourth property is the property of transitivity. So the property of transitivity states that if x is related to y, we start with assuming that x is related to y and y is related to z. If x is related to y, I can say x is equal to k1y, and if y is related to z, I can say y is equal to k2z from the definition, where k1 and k2 belong to the set of positive integers. So we have these two relations from the definition. Now, if I want to replace y using this expression, I can say x is equal to k1, and in place of y, I can write k2z. So in place of y, I can write k2z, and I can say k1, k2z is equal to x. Note that if x1 and x2 belong to the set of positive integers, automatically k1 and k1 into k2 will also belong to the set of positive integers. If you take 2 into 3, 6 is also a positive integer, right? So you can say x is equal to k times z, where k is equal to k1 into k2, where k is equal to k1 into k2, which is also belonging to the set of positive integers. That is, x is equal to kz. Now this relation, this relation matches with the definition of is divisible by as well. So essentially I can conclude x is related to R. That is, if I start with the two assumptions that x is related to y and y is related to x, if I start with the two assumptions that x is related to y and y is related to z, I can conclude that x is also related to z, which is essentially the property of transitivity. So I can conclude that the transitivity property also holds. The fifth and the final property is the property of completeness. Now, if you think of the property of completeness, it said that for any two elements belonging to the set of natural numbers, in this case, I should be able to say either x is related to y or y is related to x, or both at least. But at least one of them has to be satisfied. Either x is related to y or y is related to x. Now think of it this way. If I take the two numbers 5 and 3, is 5 divisible by 3? Can I write 5 equal to k times 3, where k is a positive integer? No, I cannot. So I cannot write x is related to y. Can I write 3 is related to 5? Can I write 3 is equal to k times 5, where k is a positive integer? I cannot again. So I cannot write x is equal to y or y equal to x for a choice. Like, it's not true for every choice. There are certain x and y's belonging to the set of natural numbers for which either of them holds, or in some cases both of them hold, but that's not true for any x and y that I choose. So in this case, the completeness property does not hold. So what are the conclusions? The conclusions are that for the given relation is divisible by, and for the given set of natural numbers, I have the reflexivity property to be true, I have anti-symmetry property to be true, I have symmetry property not to be true, I have the transitivity property to be true, as well as, and the fifth property, which is the property of completeness, the property of completeness is not true. So the property of symmetry and completeness does not hold, whereas the other three properties holds. And that is how you approach a particular sum when you need to look for the properties that hold for a particular relation.